During each second of free fall, the speed of an object does what? As I sort of disrupt you, but it's half because I'm stalling, give you more time on the first one. If you haven't noticed yet, because I haven't announced it, after the sessions, I'm now able to easily integrate back with a LMS, Canvas. So these clicker questions, since you registered through the module section, and it attaches to your name. So if you did that and bought your Turning Point license so that it's active, then I can hit several buttons and send it back to Canvas. So in the Canvas's grade book, the only thing that'll be there for this course is your clicker responses, so that you can see how you're doing or if it's working or not. But point is, your clicker responses will become available as I send them back to Canvas in Canvas, so that you're aware if you weren't. But that's the only grade in Canvas. Everything else is in WebAssign. Friendly reminder, clickers are going to be worth 10% of your overall grade. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. 44 responses today? All right. 2/3 of you think it's A, but a big section of B. The correct answer is indeed A. And those were the two I would have chose between as well. The correct answer, A, it's the same amount. That's because during each second of free fall, the speed of an object, we're seeing how the speed changes. What do we know in free fall? What's a known, something you know? Gravity, which is a what? It's 9.8 meters per second, or meters per second squared, right. That's the rate that the velocity changes. It changes 9.8 meters per second every second. So that's why it's A. The speed increases by the same amount. It is getting bigger and bigger, faster and faster, but by the same amount each time. What would be the answer to B? Changes by increasing amounts each second. It's not speed. It's not acceleration, because that's constant. What is getting bigger, but more and more each second? Yeah, the distance. Its position, it falls. You know, you let go of something, after 1 second it falls maybe a little bit. But during the second, it's now going faster. It's going to fall even further, and even further, and even further with each second. Until what happens in real life? Will it just keep going faster and faster and faster forever? Yeah, at some point it'll hit terminal velocity, that enough air resistance. The faster it goes, the more there'll be an upward air resistance force to make it not slow down, but what? Stop speeding up. Very good. Good way to put it. It will no longer accelerate. Gravity's still trying to accelerate it down, but the air resistance will try to accelerate it up. So it'll reach a constant velocity. And at that point, with no acceleration, it will not increase its speed anymore. And just for clarification, then that's not free fall. When you start taking in air resistance, it's not free fall. Free fall is only considering gravity. And so at terminal velocity, the two forces are equal. It's weight and air resistance. Hence, the net force is 0, no acceleration, not changing its velocity, and its inertia keeps it going at that same speed until something changes. It doesn't need a force to keep moving that fast. The net force is 0. It would need a net force to change its motion. Hopefully all these laws are coming together. We get to start Newton's third law now, which we've already tinkered with. Any other questions? Do you find this helpful? I like the discussion too, just seeing how it works. I had an excellent email this week that asked me about kind of a way to review for the test. And it made me think, and I want to tell the whole class that you have lots of questions that I ask you. Obviously in homework, the pre-lectures, clickers. Your textbook asks you lots of check your understanding questions as you go along. And if you didn't realize all the end of the chapter questions, there's a lot there. All the odd ones are answered in the back. But it's not as important what the answers are if you don't understand why that's the right answer. So I strongly encourage you to reason through the check your understanding stuff in the book, the explanations we do here, and the answer keys to the homework. If you don't understand why it's the right answer, you won't be able to apply it to a new, different question on the exam. Because my point is to teach you the concepts, not just, oh, it's like this in this case, and it's like this in this case. That's why I try to do all this. Okay, let's do another one. I think it's the next slide. Yep. All right, go. 2 different sized rocks falling in free fall. We dropped stuff last lecture. Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1, just in time. Oh, we gained 2 people. Good. All right, mostly C, some of D. All right. I would like you to discuss this one with your neighbor, and I'll re-ask it. Find someone that, it'll be more beneficial, find someone that disagrees with you. Try to explain to each other why you think what it is, and re-vote. I'll open it up so you can re-vote anytime you want. I'll give you a couple minutes. It's to your benefit to move and talk with someone. I'll ask a question. In D, what's it? Force to mass ratio. What the hell are they talking about? Do you realize what a force to mass ratio is? That could be, might help you with answering the question whether you want to rule it out or go for it. What's our guide to thinking between a relationship between force and mass? So what's the force to mass ratio equal to? That might help some of you. Decide yay or nay. All right, go ahead and re-vote. Let's see what you think now. We'll see if this worked. If it helped or made it worse. From what I can hear, it sounds like, in last response, most of you are debating between C and D. Does that sound... What I see different between C and D now is, let's see, C is the force of gravity is the same, and D is the acceleration is the same. That's the force over mass ratio. So you have to decide which one of those is the same, or which one's different and rule it out.
Well, last time you said the force is not the same, the acceleration is the same.
She has her vote. All right, go ahead and get your vote in. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. There's 2 more of you out there. 1 more. Come on. You're out of time. Great. 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 All right, I'm going to do a demonstration then before I give you the answer. This really is helping. You're going to remember this better. All right, I'm going to take 2 objects. One's heavier and one's lighter. We know what slows them down on Earth, right? Air. So this experiment is to get rid of the air, so we can just have free fall. One's going to have more mass than the other. So let's turn this on. This is an electromagnet that holds these 2 little shelves up, so when I release it, I can drop them at the same time. So I'm going to put 1 there, 1 here. Close it up and pull some air out. Okay, so it's a vacuum pump. I'm pulling air out. It'll take a minute. All right. Do they weigh the same? Most of you are saying no. What is weight? Speed, position, force, mass. What's weight? It's a force. What's exerting that force on them? Yeah, gravity. So that was like the C. Force of gravity. Weight. You just told me they don't weigh the same. So, what do you expect to happen when I release these at the same time? Say it a little louder because it's noisy. I can't hear you. He thinks they'll hit at the same time. Who agrees? Who disagrees? Okay, most of you. Okay, so we have to remind ourselves, why do they hit the ground at the same time? Is it because they're being pulled with the exact same force? Or because they're accelerating at the exact same rate? That's long enough. Let me get out of the way here. All right, I suggest you watch the bottom half. It happens quick. You ready? 1, 2, 3. Whew. Whew. Physics is true. They did hit the ground at the same time when you get rid of air resistance, which told us they fell at the exact same rate, acceleration. You know that they both fall at 9.8 meters per second every second. In order to do that, the Earth must pull on the ball with more mass because it has more inertia. It wants to resist its change in motion more, so it has to pull on it with more force. The force of gravity on the big ball is more. It weighs more. It's heavier. But they accelerate at the exact same rate. So the answer was D. Let me dim the light so you can see. Yeah, you're still mulling that over. What's bugging you? Because it's probably bugging someone else too. Does this get... Yeah, that's one reason I ask this. People get force and acceleration messed up, and especially with gravity, because we just say, oh, it's gravity. It's due to the force of gravity. And sometimes we say it nonchalantly. Yeah, it's due to gravity why it's getting pulled down. But there's two things that happen. There's a force and an acceleration, and they're not the same thing. So a lot of people, unfortunately, including scientists, aren't being careful, and when they talk about this, they might actually say it incorrectly. We should always say that all objects fall at the same rate. And it's not accurate to say because of gravity. And that's part of the answer. It's gravity is what's pulling them down, but it's the acceleration that's the same. The acceleration due to gravity might be more accurate. Because the force they feel due to gravity is definitely different. They have different weights. The earth pulls on me with more force than it does you, because I weigh more than you. That is my force. I have more mass. I'm sure you're happy about that. But we will both fall with the exact same acceleration due to gravity. Is that helping? Here's my actual favorite part about this demonstration. When you let the air back in, it's the sound it makes. I love that. All right. Anything else on that one? It's a great example of Newton's second law and how it comes about, how acceleration is directly proportional to force. You pull on something heavier with more force, you can get it to accelerate. Oh, let me do it. Let me do it this way. If things accelerate at the same rate, that's another way to think of this. Something with more mass and something with little mass. What must the forces be to have that same acceleration? Yeah, little force over here and a big force over here to keep the same ratio. This is exactly what we just witnessed. The big ball is feeling more force, and the little ball less. But this has stayed constant during free fall. Extension. Let's say we dropped both of them. Which one would reach terminal velocity first? Something big, something small. One vote for smaller. Yeah, let's say we just take them and drop both. No, because I do want you to consider air resistance now. Which one will hit terminal velocity in applying air resistance first? Okay, now we got more votes for small. Yes? Okay, I'm glad you mentioned that. He said maybe it could be the big one because it takes up more space. And it's something we haven't discussed in class. The book does. The cross-sectional area of an object does affect the air resistance. In other words, this is going to hit a lot of air, and so there'll be more air resistance on this than something with the exact same mass, but that's smaller. So that is a factor that I was ignoring. And so let's say they're exactly the same size, but one has more mass than the other. We'll get rid of that part for now. Which one would you think hits terminal velocity first then? The smaller one. Your guts are telling you right. Here's an example. They're roughly the same cross-sectional area, and clearly this one started hitting terminal velocity first. Again, because it has less force. So this one has a weight down, and it only takes that much air resistance to hit terminal velocity once they're equal. That'll happen sooner for the light object. Doesn't have to fall as far. Where the big, this object, I'll draw it the same size, but it's a lot heavier. Thus, it's going to need that much force of air resistance before it ever reaches terminal velocity, until the net force is 0. So it'll fall further and take longer. It still might reach terminal velocity. Once they both reach terminal velocity, who will be going faster? One vote for the larger? Larger? Yeah, larger. He's going to have to be going faster. He's going to fall further and thus increase his velocity more and more every second until this condition matches. So once they each reach terminal velocity, they won't accelerate anymore, but he'll be going faster. So clearly, this one will hit the ground first, going faster. These are good questions. I can tell we're thinking now. All right, I had one more I wanted to do, but you know what? I think I'll save that. I'll save it. You could put your clickers away if you like. Let's do two volunteers, please. Help me with a demonstration down here. Anybody like to help me? Sold. Sold. Thank you. I'm going to have you guys sit on these carts as close to these edges as possible and facing each other. So pick a cart.
Just kind of like that.
Yeah, crisscross applesauce. We're going to start Newton's third law here. You sit on this end facing him. And this is my favorite way to introduce it and get you to realize a good concept a lot of people miss. Okay, both of you put your hands up like this. Go ahead and make contact. I'm going to ask you to be a brick wall and don't move. Okay? I'm going to ask you to exert a force on him, push on him, and let's see what happens. No? Okay, I'll try it again. All right, do it again. You don't move. Don't push. Just you push. All right. You. No offense, but you be the wall. Don't move. You push. This is actually what's supposed to happen. Anybody want to guess why? Newton's third law, my favorite way to sum it up, agrees with the author. All forces come in pairs. All forces come in pairs. You can't have an isolated force. So when he pushes on him, he can't help but push back. And so both were affected, and vice versa. So even though I was telling you not to, you can't. They're in contact. Well, they don't even have to be in contact for everything. So that's our point. Now, what else did you observe when they pushed? See if you guys made any good observations. They rolled backwards. Good. They both moved. So, because if he exerts a force on him, then he feels a force that way, and vice versa over here. So they both moved. Did you notice their motion? Could we describe their motion? It was opposite in direction. That's the other part of Newton's third law. All forces come in pairs. You've probably heard for every action there's an equal but opposite reaction. They're in opposite directions. He pushes on him that way, well then he pushes back that way. Equal in magnitude, same F, same vector, but pointing in opposite directions. All right, what else do you notice about their motion? Anything? One was moving faster than it. Let's try it again. I want you to be the wall and you push. Let's see. So you guys can witness it again. Yeah, he's not moving quite as fast as he is. Why? I just told you they're feeling the exact same force. Do you believe me? No. I'll tell you, they are. That's Newton's third law. The force that he felt is the exact same force he felt. That's Newton's third law. So why did he move farther and faster? Exactly. Who has more inertia? No offense. So something with more mass will accelerate less for the same force. Does that make sense? I'll draw that one up too, but while they're still here, try it this way. Here, feel this. Oh, actually, that one's getting old and it'll probably bust. Feel this. Feel this. All right, this time I'm going to have you throw the ball, toss it to him. He's going to catch it, and then you immediately toss it back, and we'll do that as often as we can. Very good. That worked out great. All right, give him a hand. Thanks for helping. Appreciate it.
Yep.
Thank you. Did you observe the difference in motion again? He moved further. It had a larger effect on the object with less mass. So we can do this same game. But what's staying constant this time? What was the same on both of them? The force. So this time we're going to do it this way. Exaggerate. Because Newton's third law says the force on him was exactly the same amount as it was back on him, just into opposite directions. So if we want to see how, you know what, like it matters, but they were sitting like this, so maybe it'll help you keep it straight. So him. If we want to see how is his motion changed, change in motion, acceleration, we get a little a. Now let's look at the motion of this person. We look at the force on him, it's the same, but he's got less inertia, so he's going to accelerate more and change his velocity more. Make sense? So I use Newton's the three laws together all the time. Newton's third law helps us set up this one to understand what's happening. But Newton's second law, relationship, tells us helps us understand how they're going to react. All right. Another thing to notice. When he threw the ball, did you notice what happened to him? He moved back. So something's going on there too. If he exerts a force on the ball, if he exerts a force on the ball, then Newton's third law says all forces come in pairs. The ball must be exerting an equal but opposite force back on him. And to help you, I warned you at the beginning of the semester, and here it comes up again, and especially the horse and cart homework problem. If you haven't seen it or worked on it yet, it seems to trip people up every semester. That's why I keep asking it. It's a good teaching tool. If you want to understand the motion of an object, only consider the forces on that object. So that's why I drew it like this. This one's on the ball. This one is on him. So that's why he recoiled. The ball pushed him that way. Likewise, over here. The ball was coming in. What did he exert on the ball to stop it? The force. What did the ball exert on him, back on him? The force. And that's why he went this way. And then he threw it and recoiled again. Every time they caught it or tossed it. These are what the scientists call action-reaction pairs. Don't really think of it as, oh, this was the action, so this was the reaction, because it really doesn't matter. That's why I like all forces come in pairs. Here's two examples. Action-reaction. Action-reaction. Everything comes in pairs. But the clincher here, are you perking up now? If you haven't been, listen now. They're always on opposite bodies. An action-reaction pair is never on the same object. You see that? So here's a good question. It's kind of tricky. All right. I stand on a bathroom scale. I didn't bring one out. We'll say this is the scale. And I measure my weight. That's great. Okay. What's pulling me down? Gravity. Right. It's the force due to gravity. It's a force down. Okay, if that's the force on me down, what's the other pair in the action-reaction pair? The scale, me pulling the earth up. Did I hear somebody say the table? This is how it can get confusing. So I always like to think of it this way. What's pulling me down? Yeah, and what's causing that? The mass of the earth. So the earth is pulling on me down. So the pair is I pull on the earth up. That's the action-reaction pair. Which can be confusing because you're like, wait a minute, it's pulling me down, but I'm not moving down. Why am I not moving down? Because the table and or the scale are supporting me. But pay attention to this. The earth pulls on me down. The table or scale push on me up. Both are on me. That's your clue. They can't be an action-reaction pair because they're both on me. They'll both affect how I try to move. So we actually have two pairs going on here. The earth pulls on me, I pull on the earth. That makes me run into the scale and the table, so I'm pushing on the scale. The scale pushes back on me. Me on the scale on me. Another action-reaction pair. You with me? So next time you might be feeling bad or not strong or something, this is good for self-esteem. I weigh about 160 pounds. That means the earth is pulling on me with a force of 160 pounds downward. Ah! Well, from Newton's third law, what else can I say? How strong am I? I'm pulling on the earth. It's attracting me down. I'm pulling it up with a force of 160 pounds. Yes. It's true. Who believes me? Get your hand up because I'm not lying. I'm not trying to trick you. But you're like, but who has questions? Wait a second, that doesn't seem right. Who can explain it now? It's the action-reaction pair. They all come. It pulls on me with 160 pounds of force. I pull on it with 160 pounds. Yet I'm the one that moves. Does the earth move? I don't know. Does mass have anything to do with it? Absolutely. It has everything to do with it. So it's essentially this case, but let's exaggerate. Here's me compared to the earth. So yes, the earth moves. This much. Because it's so massive. I have hardly any effect on it. It's the same force, though. I am still pulling it with 160 pounds. But it's like, so what? It's got all this inertia. I'm puny compared to it, so of course it accelerates me down. So that's Newton's third law, an action-reaction pair. What do we got, 10 minutes? Let's see here. You don't need to project this one. Wake up. I have our pre-lecture questions up. So one says, the force that propels a heavy truck along a highway is provided by what? The correct answer is as follows. I'll get up here so you can see better. It's kind of like you walking and running. The car's trying to move that way. So the engine turns the wheels and everything. And what do the wheels push against? The ground. It's like when you try to walk. You're trying to walk this way, you push against the ground. Hopefully you don't slide. If I'm like this, which way am I going to move? Oh, yeah. So the ground must be exerting a force on me that way, or I wouldn't be moving. What's the action-reaction pair? Ground on me, me on the ground. Right. We like to think of it as I push on the ground, so the ground pushes on me back, and I can move forward. So it's the ground. And that goes, it said the highway. It's your car, it's actually the ground pushing against the tires, back on the tires to propel you forward. Your engine provides that force to push against the ground, but it's the ground that actually pushes the car forward. Does that make sense? Your second question was, a boulder falls due to gravity. The reaction to the force on the boulder is, we just did it. So you got a boulder that's falling due to gravity. Earth pulls on the boulder. The boulder pulls up on the earth. Is the action-reaction pair. Yes, it meets air resistance, and that retards its motion. That forms a different pair, because the air resistance is on the ball. Earth is on the ball. The action-reaction pair can't be on the same object. That'll help you with a lot of these questions as you're working through them. All right, now for a, let's do, let's stay with this. People tend to have trouble with this one too, so I wanted to go over it. Okay, I'm going to punch these. And I can punch this. If I try to swing the same, not much, right? All right. So I'm swinging my arm at the same rate. I'm attempting to. Which one would you rather be? If these were your face, would you rather be this or this? You'd rather be the... Okay, we got both answers. This is good. Why the medicine ball? Your face would have more inertia, so it would have less effect on you. Your face wouldn't accelerate as much then, right? Okay. Something to do with balance and the fact that this impact isn't as large as this impact? Something in your gut tells you that? Okay. Good logic for both. Let's analyze these. Okay, if I hit this, we got a force and a force, correct? Action-reaction pair. All right, and my hand. So my hand exerts a force on the ball and tries to move it. So this is hand on ball. So it must be an equal and opposite force back on my hand, correct? Ball on hand. You're like, yep, okay, got it. So what, Adam? We can do the same game with this one. You don't have to draw it yet if you don't want. Basically, we're going to get, you know where I'm headed. Hand on paper, paper on hand. The question is, how do these forces compare? You know, if this is your head, whichever has a smaller force, we would like that to be our head, right? Likewise, though, whichever one's the smaller force will hurt our hand less. Correct? So let's look at that. Let's say I were to hit these harder, as hard as I possibly could. You know, whoosh, versus whoosh. Which one's going to hurt my hand more? Bet that one you have a better feel for. The medicine ball. True. Why? It's for his same reasoning. It's got more mass, it's got more inertia, it wants to resist changing. Yeah, so it's going to resist that motion more. And you're correct. Hitting that one will require more force. So the flip, according to Newton's third law, even though maybe we didn't understand it before, if we understand this side, it's got to have more force on the ball. And that is the case. I'll go ahead and give you the answers. So to emphasize, I'll draw these shorter. They're still equal and opposite here. They're still equal and opposite here. But this one is going to hurt more, both sides. Why is that? This one bugged me for a while too. That is, because this doesn't give, it allows me to push on it more. It's kind of like I can push on it, push on it, push on it. I keep pushing and push it, and then finally starts moving. I have to exert more force to get it to move. I think you agree, understand that. So it will let me push on it with more force before it has an effect. What about this? If I start pushing on it, it starts moving out of the way, doesn't it? Let's look at this case. I'm moving at a constant speed, yes? Tell me what you know then. If I just push on it with a constant speed, I can be extended even. The speed's constant. Tell me what you know. The change in V is 0. It's not changing. Boom, you should know lots of things now. Yeah, that means the acceleration is 0 on the filter. And I'll even be the net acceleration is, which also means what? The net force must be 0. But you know I'm pushing on it, so two forces must be balanced. But I'm not pushing any harder. Basically, it's wussy, so it can't push back. It'll either break or just kind of move out of the way. Take another extreme. I can hit this as hard as I want. Anybody want to do that here? Because it won't move. It'll push back harder than this is able to push back. Does that help you maybe see why it's still the same action-reaction pair, but you can't exert as much force on it because it has so little inertia? Life lesson then. You're getting hit in the face. What should you do? Yeah, duck is best answer. But let's say they actually make contact. Accelerate your face in the direction of their fist. Absolutely. Okay, you didn't get out of the way in time to miss the fist. But maybe you can get out of its way as it's trying to hit you. You know, your gut should make sense with this. Would you ever want to do this? Go to meet it? No. Yeah, so that you could hit there. And if you're trying to be a rock, it's like the brick wall. And it's going to exert more force on your head. Maybe your only satisfaction is that, yeah, but it also hurt his fist more. Because it's equal and opposite force. He's going to break his fist. Meanwhile, you broke your face. So, yeah, if you move out of the way, you're not letting him increase the force anymore. You're still feeling the same force he's pushing on you, but he can't push on you with as much force. I think that one's fun. Groovy. Any last-minute questions? I want to remind you then, before you pack up, if you didn't realize yet, I hope, you have your first exam next week. Today's Wednesday. It's next Wednesday. We will finish up Chapter 5 on Newton's third law Friday. You'll have a homework due on that Sunday. we'll review Monday, everything, and have an exam Wednesday. Lest you didn't realize. All right. See ya.